Today we're going to be looking at here's a libc from picoCTF. The challenge gives us a vulnerable executable, the libc version, and the makefile. And the hint tells us to look at pwn-tools, and maybe something there will be of help. So I've downloaded the targets here. Notice that when the challenge gives you a libc version, it probably means something important. So the first thing that we need to do is find the appropriate dynamic linker that's coupled with this libc version. So we could do this with some Google foo, but the PwnNet program that I covered in a previous video really makes it easy. And I'll add a link to the description below. It'll automatically download the dynamic linker for you and patch the target to use both that and the specified libc version. So let's try that. So I'm just going to run PwnNet. And so it sees that we're in this directory and sees that the executable is vuln. So it outputs the dynamic linker here, the LD TAC 2.27, as well as creating this solve script for us and then the patched executable. So now we can run vuln patched and it just says welcome to my echo server and seems to give us back the same thing that we typed in. Okay, now that we know that we can run the program, let's get some information about how it was compiled. We could take a look at the makefile. But I really like to run checksec, which is installed with pwn-tools. Okay, so it looks like we have partial relrow, no stack canary, NX is enabled, meaning that we can't execute on stack, but it's not position independent. Okay, so this will be great to remember once we find a bug in this program. Okay, so we've imported this program into Ghidra, and I like to start by going to main here. So we'll go to the decompilation here of main. We see that it's doing some stuff with some static strings and this convert case function, but it's really just doing this do stuff in a do while loop. And so looking at this, we see that it's calling scanf for user input up and until there is a new line. And it's storing this data, this user input, on the stack in this buffer that is 112 bytes. And since scanf doesn't limit the number of bytes that we can nab from the user, we can overflow this buffer and control the return address of the program. So given that this was compiled with NX enabled, we can't just overwrite this address and return back to our stack where some shellcode lies. And even if we could, it looks like this program is calling convert case on the first 100 characters. So our input would be modified, meaning that our shellcode probably wouldn't work as intended. So that means that we're going to have to execute somewhere else. And this is kind of keying us in to look for some ROP things. So now let's try and see if we can crash the program. We've verified that we can run the program, but we didn't see if we can crash it. So if our theory is correct about this bug, we should be able to give it over 112 characters, and something should happen. We should get a segmentation fault. And so I'm just going to put in a lot of A's here and hope that this is more than 112. We could optionally just do this with Python, probably be a lot easier. Okay, so we got a seg fault here, so we know that we can crash the program. And now we need to figure out the offset to the return address. So we need to figure out exactly what bytes are going to be stored there, so that way we can use this to jump to an executable place in the program. So we could do that by looking at the Ghidra stack layout right here, or we could use Python and have it do the hard part for us. So since I'm bad at math, let's go ahead and just try it out with Python. So I've opened up the solve script that PwnNet automatically created for us, and I'm just going to load that into an interactive Python shell because I think that's going to be a lot easier and helps me to remember a lot of the different pwn-tools, methods, and things like that. So let's try that out. It would help if I'm actually typing in the terminal. So here we go. We got Python tac I, and then we'll give it solve. Okay, cool. So it's running some stuff for us. We see it runs the checksec stuff, and that's because PwnNet did for us, it declared that these elfs were being used by the program, right? We have a program and our two shared libraries that we're going to be using. Okay, so the first thing that we want to do is we want to create a cyclic pattern. So what this will do is generate like A followed by A, So let's create our cyclic pattern here. And let's just create one that's, I don't know, 256 bytes. Okay, and so if we print that out, you kind of see what I'm talking about. So we have 4 A's here. Okay, so I had it backwards. Followed by a B and then 3 A's, followed by a C and 3 A's, so on and so forth. So each 4 characters are unique. Okay, and so now let's go ahead and run the process. So we'll do a process, and then we'll give it the path to the executable. So we can say exe.path. Okay, so we've started the program. And now we're going to send our cyclic pattern to the program. So we can say something like proc dot, we want to send, and just to confirm what this program does, if we do a vuln.patched. Okay, so it says, welcome to my Echo server. So we want to send our data after that. So I'm just going to copy this here. Okay, so we'll copy this, and then we'll do a send line after we receive this data, and it's going to be in byte notation. So we're going to do that. I'll paste that in here, and then we're going to say our payload. Okay, so we've sent that to our program, and now we just need to wait a little bit. Okay, so the process stopped with a seg fault after it processed our input. And now we want to get the core dump of our process. So if we do proc.core, core file, this will automatically search for the core dump from the file based on your system and what architecture you're using. This can change. But Pwntules does a fairly good job of trying to get it. Okay, so now that we have the core dump, we want to search our core dump at the faulting address for where it lies inside of our cyclic pattern. So if we do something like, let's say fault is equal to our core dot fault adder. Okay, and let's just examine that. Let's see what that produces. Okay, so we have that, but we want to view it in terms of what characters are there. Okay, so these are the characters that were there, and now we just need to search for those characters inside of our cyclic pattern. So we can do something like offset is equal to our cyclic find, and then we're gonna give it exactly what we just gave it. So the core dot faulting adder. Cool. So let's see what our offset is. Okay, so our offset is 136. Cool. So now we know exactly how many bytes we need to send to the program before we send an address that we want to jump to execute. Now that we know where the address needs to go, we need to figure out what address we want to put there. So a good guess would be to use system with the arguments of binsh, and that would allow us to open up a shell on the remote server and then cat the flag. So let's see if we can find those inside of our executable, or rather our shared objects. So the first thing I'm going to do is I'm going to call ROP is equal to ROP on our exe. So this will give us a ROP object that we can work with. And then I'm going to get a generator for libc. So we're going to search libc, and we're going to search for the bytes /bin /sh, and we're going to see if that produces anything. So bin sh is equal to our generator, and get the next object. Okay, so that worked. So we are able to find bin sh in the program. So this will be the address of where that is at. And now we also need to figure out if we can call system as well. So let's see if we can get that. So if we do a ROP.call, well, before we try and call anything, let's try and just search if we can get that. So we'll do a libc, and we'll search for our symbol for system. Sorry, we don't actually want search here. We want our symbols. We're going to do libc.symbols. This will give us all of the symbols of the program, but we specifically want our system. So let's see if this actually returns anything. Okay, so we do have that. So we would be able to do something like a rop.call. Well, let's turn this into a variable first. Now we can make our function call by doing something like a rop.call and then pass in our system followed by our business h. And I messed something up here. Yes, that's because this is not just one, but it should be iterative. Oh, no, other way around. Sorry. Okay. So now let's dump our Okay, this is very easy then. So yeah, we could try running this. So all we need now is to offset this with our offset from before. So we know that it was 136, or we have it offset here. And then we want to put our ROP here. Okay, and so now if we dump this again, oh, sorry. Okay, so now we have our ROP chain, but it is preceded by our offset that we figured out before. Okay, cool. So maybe we could just send this to the program and see if things work. So we'll run what we ran before, except this time we're going to we're not going to send our payload. We're going to send our ROP chain. So we'll do our ROP chain. Okay, welcome to my server. Okay, and we didn't get anything. Well, why is this? Well, although we did look up where system was in libc, we don't actually know the runtime address of libc, right? Because it's going to be loaded in memory at a specific, virtual address, and we don't know ahead of time what that's going to be. So what we actually need to do is we need to create two ROP chains. We need to leak an address from libc to tell us where libc is going to be loaded. And then we need to use this ROP chain to actually call our shell, right? So the next step, we're going to focus on leaking an address. So taking a look at our executable again, let's look at where one of the libc addresses is inside of the PLT, the procedure linkage table, and the GOT, the global offset table. It doesn't really matter what function we look at, but let's take a look in Ghidra at something that's going to be inside of libc. So we could choose something like scanf. We could choose something like puts. These are all going to be functions that exist inside of libc. So for just a simple example, we're going to choose puts here. And that's what we're going to roll with. So let's examine where puts is inside the PLT and the GOT. So to do that is really easy. We can just say puts PLT is equal to our exe.plt, and then give it the symbol that we want to look up. So we have puts. Okay, and now we need to do the same thing for the global offset table. And just as a reminder, that the PLT is a readable section of memory that will jump to the global offset table to call a function. The global offset table, by extension, is a writable section of memory that will look up the function pointers via the dynamic linker the first time that it's called. And after that, the global offset table will write that address inside of the global offset table, so that way it doesn't have to keep using the dynamic linker to look up these symbols. So the clever idea here that we're going to do to leak an address from libc is we are going to create a ROP chain that will call puts with the address of puts as the argument. So this will print out the address where puts is loaded inside of Libc. And then from there, we can calculate the offset, i.e. the base address of Libc. So let's try that, knowing what we know now. So again, I'm going to do this ROP. So the first thing that we're going to do is we're going to call puts. And the address that we want, the address that we want to print out is going to be from the global offset table, because this is where it's going to reside. Or this is where dynamic linker resolved puts to be. Okay, so we could just do that. But the other thing that we need to do is to continue the execution, because the next time that this runs, that address might be different. There's a good way to have this repeat itself. And that is, we can just call do stuff over and over and over again, right? Because it's inside of that do while loop. So let's add that to our ROP chain as well. And we can do that really easily just by doing rop.call, and we can do stuff. And really like that we have symbols. Okay, so now we can create our ROP chain again. We'll do, we'll add our offset chain here. That would be because I should have said ROP here. See, I make lots of mistakes, and so can you. So now if we print out our ROP chain, now we should see something that resembles some actually executable part of code. Okay, so now let's try sending this to the program and seeing what happens. Okay, so we'll start the process again. And we will send our ROP chain this time. Okay, so we're going to send our ROP chain after we get that welcome to our echo server. And then we want to receive 2 lines. So we're going to do a proc.receive line. We get a new line character, and then we get the output that the echo server is printing out to us. And now if we get the next line, this should be our address of puts. So we're going to store this inside of a variable. We'll say like puts adder is equal to our proc.receive line. Okay, and if we print that out, then we should have the address of puts, and indeed we do. We now just need to actually convert this into our like an integer that we can then pass later on. So I'll say our puts adder is going to be equal to int, and then it's going to be from our bytes. So the puts adder itself. And then we're going to say the byte order is going to be little. And it would help if I could figure out what I'm doing wrong here. Let's see. Oh, yes, extra parentheses here. Although I see now that I actually have a mistake here. I don't want this /n here. So that could actually throw things off. We want to get rid of this new line. So yeah, let's redo that. So we'll do a okay. So we want that instead of our puts adder. And if we print that in hex, cool. So this is the address of puts. now we can calculate the base address of libc. So now if we do something like libc.address is going to be equal to our puts address that we just found out, right? And then we want to subtract the where the symbol puts is inside of libc. So we'll say, oh, I really can't type today. Puts and if we print that out as hex, this is our base address for libc. Okay, so now what we finally need to do is to call our ROP chain that will land us a shell on the system. And that's what we did before. That didn't work because we didn't have the correct base address. So now we kind of need to redo that work. And yeah, from there, we should land a shell. So let's go back and call system with the argument binsh. Now let's go ahead and revisit our ROP chain that we'll call system. So let's start from the top. We'll create our ROP object again. So we'll do that, and then we'll create our generator again. So we'll say libc.search, and again we're going to search for binsh, and that should be as bytes. Cool. And now binsh should be the next one. Okay, so it did find one. Otherwise, it would give us a stop iteration error. And the next thing that we need to do in our ROP chain in order to align the stack is to call puts again. So let's do that. So we'll call puts, and again, we'll just print out the address of the global offset table from before. And then the next thing that we want to do is we want to call our libc.symbols and then system. And then again, the argument that we're going to pass in is our binsh. Cool, that looks right to me. And now if we print that out, this is the ROP chain that we're going to do. Now we just need to fit this inside of our offset. So we'll say, again, we'll do our ROP chain. Well, yeah, we'll do ROP chain 2 is equal to offset ROP. Okay, so now we just need to send this to the program because we should still be running the process in the background because we never received any more lines, and it should be accepting another line. So yeah, let's go ahead and try that. So now we should just be able to send it to the program and have it work. So we'll do a proc send line, and then we'll send our ROP chain to. Cool. Now let's see what we get back. Okay, so we got something else back. And we got a segmentation fault. Womp, womp, womp. Okay, so I actually went in and tried to debug what the issue was with this. And it appears to be an issue with my local machine. So we're going to redo what we just did, except this time we're going to do it on the remote server because I think. All right, and so through the power of editing, we have arrived now back at the same location where we were after we've already sent our first ROP chain, which leaked the address of puts here at the runtime address, which allowed us to calculate the base address of libc, which we can see here. And now we've generated our final wrap chain, which will now call system with the argument of binsh, landing us a shell on the server. So now all we need to do is we need to send this over to the server. We can do that by saying our .send line, and now we can send our wrap chain. Cool. So now I'm just going to receive some items here. So we'll do a receive line. We'll do another receive line. And now hopefully we have the shell. So if we do something like a send line, and we send like, I don't know, cat flag.txt, we should get something back. So our flag is going to be that, which we receive. And if we print that out, we should get our flag. I hope that this was informative, and I hope that you learned something. If you have any other questions, please feel free to reach out to me. You can take a look at my GitLab, which is linked below. But other than that, I hope you have a great day.